Alright, silly people, here's the situation. We have a function which generally describes a classical probability distribution, um, obeying classical physics of being 1 over the velocity at position x um, times the period of its motion. Um, so, what we're going to do is we're going to, first of all, express the velocity um, in terms of the total energy of the system and the potential energy of the system at position x using conservation of energy, which is just saying that the total energy of the system at any given time is uh, the kinetic energy plus the potential energy. Um, we can solve for the velocity then as being e minus v, and then you're dividing by m and multiplying by 2 and square rooting it. All right, so that's your velocity in terms of e and v of x. We can also go ahead and rewrite our probability distribution now, if you want, as being 1 over t, and then this is not minus 2, it's times 2. Be clever with that one. And then you'll have just the square root of m over 2e minus v minus 2v 2v of x. That is your most general probability distribution. Now, we're going to be finding the probability distribution specifically for the harmonic oscillator. The harmonic oscillator has a potential energy equal to kx squared over 2. So we're going to say that our probability distribution is 1 over t square root m over 2e minus kx squared. And that's as simple as it gets, I think. And we need to check that it's correctly normalized. So we need to find the integral over a complete cycle of the probability distribution over position and prove that it's equal to 1. Now, a full cycle for an oscillator like this is going out and back again one time. So half of the cycle is just going out. So if we just multiply by 2, then the integral from its starting position, one extreme to the other extreme, of the probability distribution. So it's root m over 2e minus kx squared dx. We should find that that's equal to 1. So how are we going to do this? So let's factor out m over a square root of m over 2e. Right, so we got 2 over t out front. We got the square root of m over 2e. And then inside the integral, we have 1 over the square root of 1 minus kx squared over 2e. and that's being integrated over position. We're going to make a u substitution where u is equal to just 1 minus kx squared. No, that's not going to be any good. The u substitution is going to be x times the square root of k over 2e. So that du is going to be just dx times that constant, k over 2e. I'm going to throw that into our integral. So now we're doing, it's going to be 2 over t times root m over 2e times root 2e over k. And then we're doing the integral from x0 to x0 of just du over the square root of 1 minus u squared. And that is actually a, that's a table integral. It's an arc sine. So simplifying the prefactor, the two e's will cancel out. So you have 2 over t root m over k. And then it evaluated to the arc sine of u, and then minus x naught. X naught. Let's talk about what x naught actually is. So it's defined by the turning point of the harmonic oscillator, where the energy is exactly equal to the potential energy at that point. It's still. So it's k x naught squared over 2. We can solve for x naught as being the square root of 2e over k. Okay, so plugging that into our integral, we have 2 over t root m over k and going ahead and evaluating at the endpoints, we have the arc sine of root 2e over k times root k over 2e and then minus the arc sine minus root 2e over k root k over 2e. And so obviously the insides of those arc sines both simplify to 1 and negative 1. So we have the arc sine of 1 and the arc sine of negative 1, which are just pi over 2 and negative pi over 2 radians. So we found that it's 2 over t, 2 pi over t times square root of m over k. How is that equal to 1? Well, you see, the period for a harmonic oscillator, or for anything really, is defined as 2 pi over omega, the angular frequency of your oscillator, where the angular frequency of your harmonic oscillator is just the square root of k over m, right? So we actually have 2 pi over 2 pi um, divided by omega, and then this is 1 over omega, and then the omegas will cancel out, and the 2 pi's will cancel out, and you get 1. Sick. So the harmonic oscillator is correctly normalized, so now we need to find the expectation value of position, the expectation value of position squared, and the standard deviation. So position, using the same simplifications that we used before, is going to be 2 over t times root m over 2e from x naught to x naught, and then we have, now we're just doing the probability distribution with an x up top. And this is still 1 minus kx squared over 2e. Right. This integral is a little bit more simple. You can say that u is equal to 1 minus kx squared over 2e now. So the du is equal to 1, nope, it's equal to kx over e dx. And so throwing that in, we have the expectation value is root 2 over t m over 2e, and then just e over k, and then this stuff in here becomes, we're dividing by x, so we get a, I just realized I'm bleeding over into my last line. It's du over the square root of u. So simplifying the prefactor a bit, 2e over kt, root m over 2e. We're taking the integral of, we're evaluating 2 times root u. That's how that integral works. Factoring out 2, we can have 4e over kt. We're doing m over 2e. And then, remember our u this time was 1 minus kx squared over 2e. Which we're going to be evaluating at the endpoints. So, and then the endpoints were, remember, just equal to the square root of 2e over k. And so if we square that, it's going to be 2e over k. And you'll find that when we evaluate at the endpoints, you just get the square root of 1 minus 1 minus the square root of 1 minus 1, both of which are 0. So you find that the expectation value of x is 0, which makes sense. It's a harmonic oscillator. It's swinging around the origin like this. And so on average, you're going to find that the position of your particle is going to be at the center. So perfectly intuitive there. For x squared, though, this is when things get a little bit freaky. Because now we're doing 2 over t square root of m over 2e We got the integral from minus x naught to x naught. We have x squared dx. We have the square root of 1 minus kx squared over 2e. For this guy, we're going to say a trig substitution. So we want kx squared over 2e to look like sine of u. No, you want this to be sine squared. That's right, we need that to be sine squared. So we'll take the square root first. So we'll have root k over 2e times x. And this is sine of u. And then the derivative of that is just this constant k over 2e. And then equal to cosine u du. Okay, using this we can get a form for x squared, by the way, which is going to be 2e over k times sine squared u. So looking at our integral, we have 2 over t, we got root m over 2e, we got root 2e over k, and we got just 2e over k, not in a square root. And then the integral is now sine squared u du times cosine u over square root of 1 minus sine squared u. Now, 1 minus sine squared u is just cosine squared u. That's a trig identity. And so you find that this term cancels out this term. So simplifying the prefactor, 4e over kt root just m over k. This guy again. Now it's the integral of just sine squared u. I'm going to use another trig identity. Another trig identity of it being just 1 minus cosine of 2u over 2. And factor that 1/2 out. Like that. And then we just get u minus sine 2u over 2 from minus x naught to x naught. Okay. So the sub that we used in this was this guy up here, which we can rewrite as u being to the arc sine of x root k over 2e. Our positions at the extremum of the harmonic oscillator was root 2e over k, and so u is going to be, or u naught is just going to be arc sine of 1 again, which is just pi over 2. And then we're multiplying by 2 for each of these. So we're going to have 2e over kt square root of m over k. We have pi over 2 again. We got minus 1/2 sine of pi. We got minus negative pi over 2. We got plus 1/2 sine pi. And then sine pi is 0 anyway, so bam, bam. So we get just pi again for that stuff. And then if you expand the period again, you're now doing 2e over k times 2 pi. This is pi up here. 2 pi over omega. And this is 1 over omega. The omegas cancel out again. The pi's cancel out, the 2's cancel out. So it's just e over k for the expectation value of x squared. Neat. Okay. So finally, we can calculate the standard deviation, which is going to be the expectation value of position squared minus the squared expectation value of position. We just found the squared expectation value. No, we found position squared. So it's going to be root e over k minus 0. So it's root e over k. Cool.